So I'm very happy to be introducing Jonathan Siegel, who's visiting here from Texas A&M University, the math department there. And Jonathan will tell us about continuous invariant neural networks via weighted frame averaging. Thank you.
Thank you very much. I want to thank the organizers for putting together this very interesting workshop and for giving me the opportunity to speak here. And yeah, today I'm going to talk about a method that we've been studying and developing for taking a neural network and making it invariant to certain physical symmetries. And this method is called weighted frame averaging. This is joint work with Nadav Dim and Hannah Lawrence. Nadav is a professor at the Technion and Hannah is a postdoc at MIT. Okay, so first let me just kind of introduce the background, what we're trying to do. Then I'll talk about the general problem of creating invariant neural networks. Then we'll get to some issues with previous approaches and the solution that we came up with called weighted frames, which is the important thing about them is that using these you can ensure not just invariance to the desired group action, but also continuity of the neural network function. Then I'll show an experiment which kind of indicates the utility, indicates how this approach can be useful. Okay. So, recently, of course, neural networks have been very widely applied to scientific problems. Probably the most famous is, of course, AlphaFold with protein folding. But there are many other examples, especially of applications to physics and chemistry. And here is just a schematic showing roughly how some of these methods, for example, will work. Is right, you take some configuration of atoms, right, some molecule or material, encode it in some way, push it through your neural network, and try to predict some property of importance, like, for example, formation energy or something like that. But there are many different variations on this. And of course, when applying neural networks to these physical problems, right, there are certain things that we know, right? The underlying physical laws typically satisfy some symmetries. For example, could be translation invariant, rotation, or equivariant, rotation invariant, right? So the ground truth here, the point is the ground truth satisfies some symmetries that we typically know, like be symmetric to translations, rotations, orthogonal transformations, or the action of permutation on some set of particles. There are many examples here. In this talk, I'll actually just focus on the middle three here: rotations, orthogonal transformations, and the action of the symmetric group. And I'll describe this more precisely in a second. But the point is that we would like to build these symmetries into our neural network function because that should allow us to generalize better and use less data. Another thing that we typically know in most applications, the ground truth should be continuous. Small changes to your molecule should not have dramatic changes to its properties usually, but that again depends on the precise application. So I'm sort of saying that most of the time you're going to have invariance to some symmetries, and most of the time the ground truth is also going to be continuous. And we should try to build these symmetries into our neural network architecture if possible, because and continuity in our neural network architecture if possible, because this should improve the generalization error, reduce essentially the amount of data we need. We should build all the knowledge that we have into these models. Okay, so the specific situation I want to look at today, focus on today, is the situation where the input to your neural network is a point cloud. Okay, this is just literally a list or a matrix whose columns are n positions in Rd. D is in an application would most likely be 2 or 3, but we'll consider general input dimensions and a general number of points n. So here you've got some set of d points in Rn. Okay, this is going to be the input to our network. And because these kind of represent points in Rn, the symmetries that we're going to consider here are the actions of rotations or orthogonal transformations, right? By this I mean acting on the entire point cloud simultaneously, so just the right action on this matrix by an orthonormal matrix or rotation matrix, and the action of permutation, the left action of permutation on this R d by n matrix, which corresponds to permuting the points. So this is essentially consists of, say, n identical particles in Rd, and the identical particles is captured in the fact that we want things to be invariant or equivariant to permutations, and the rotation action corresponds to the fact that our output should be invariant or equivariant to rotation. And I want to distinguish between SOD and OD, so the case of rotations and the case of orthogonal transformations. They are a little bit different, and in practical applications, you may want to actually pick one of the two. Your physical laws may not be invariant under reflections. For example, some applications to say biology or chemistry, some molecules are chiral, and at least the interaction with a biological system could depend upon whether you have the right or left version of the molecule. So in fact, perhaps the function you're trying to predict may not actually be reflection invariant, is my point. So I want to consider both of those. And these are the three actions I'm going to consider going forward in the talk are d by n point clouds with the actions of permutations, rotations, or orthogonal transformations. And you can combine these and consider the simultaneous action of permutation and rotation or orthogonal transformation. And these actions commute, so this would be the action of the product proof. We're not going to talk about this, but it's not too difficult to go from what I'll present to that, but just to mention that that's possible. Okay, so what is the goal here, right? So when we say that the function we're trying to learn is, or we're saying that our physical system has certain symmetries, what we mean by that is that the prediction function that we're trying to learn is equivariant under the action of this group G, right? G here is, as I described, right, orthogonal transformations, rotations, or the symmetric group. And just what that means, I think you're probably all familiar with this, right? If you have a group acting on two sets and a function f from x to y, it's called G equivariant if it commutes with the action of G. In the special case where the action of G on y is trivial, we say this is called the G invariant function, so the value is the same for all elements in the orbit of x. And in the talk today, I'll focus on trying to build G invariance into these neural network functions as opposed to equivariance, since it's a bit simpler and we have the strongest result in this case. Okay, so our goal here is we would like to construct some neural network function parameterized by some parameters theta, which is G invariant and also universal in the sense that any continuous G invariant function can be approximated to arbitrary accuracy. So you're not, you're able to represent everything that you might need to. Okay, so let me begin by talking about some approaches to doing this, and then we'll talk about kind of the approaches that I want to study in more detail. So there are a bunch of different ways of doing this. It's of course not a new problem. There's a lot of work on this. And one thing you could do is you could design specialized architectures which parameterize invariant functions, so that no matter what the values of your parameters are, the function you get is always equivariant or invariant, and in such a way that this architecture is also universal. For example, things like CNNs are translation equivariant. This is probably the first example of such a thing. But there are also, for example, for the action of permutations, there are very good invariant architectures, equivariant architectures called deep sets was, I believe, the first one, and transformers are also permutation equivariant. For rotations, it's a bit more difficult to construct equivariant architectures. It's been done, but they have some drawbacks. They're a bit computationally expensive to actually apply. So essentially the results, I won't actually talk about this particular way of doing it. I just want to mention there are other ways of solving this problem. So designing specialized architectures is difficult in the case of rotations. Another thing you could try to do is to calculate some separating invariance. So basically calculate some features of your input that are invariant to the action of your group and that separate orbits, right? And then essentially plug those into your neural network. For example, for the action of the orthogonal group, you could take the set of all pairwise distances and feed that into your network. This would be a way of making it invariant. So these two approaches have been studied quite a bit, but I want to consider a different type of approach to building invariance into neural networks, which may be useful in certain situations where these don't work very well. And that is methods based on transforming the input and averaging. The simplest example of this is what is called group averaging. This is also something very standard in group theory, right? Given a non-invariant neural network architecture, right? So some f theta, which represents some set of functions that are not necessarily invariant, you can make the function invariant by saying, well, I'm going to just average over, given a specific input x, I'm going to average over all transformations applied to x, right? So this will, of course, give you an invariant function, and it's also a projection, right? So if f is invariant, then this group average is going to be exactly the same as f, and it's bounded in, as a map from L infinity to L infinity, and so this implies that if f theta is a universal architecture, this easily implies that if f theta is a universal architecture, then this averaged f theta is universal for invariant functions, so it can approximate any invariant function. It's arbitrary accuracy. And an additional interesting thing about this approach is it preserves all the smoothness properties of f theta. So if f theta is k times differentiable, then this average function is also k times differentiable. If it's continuous, the average function is also continuous, right? Or continuity of differentiability, I mean, in terms of the R d by n vector space.
So can I ask,
Yeah.
what do you mean by universal architecture?
So I just mean it can approximate any continuous function on a compact set to accuracy epsilon. Yeah. But so one drawback of this approach is that it's kind of not super efficient if G is large. I mean, for example, for permutations, you'd have to average over the whole entire n factorial permutation group. And if G is infinite, you can't even implement it exactly. So what you could, of course, do is instead of evaluating the integral in 5 exactly, you could sample from it. And this essentially is data augmentation. But, okay. Yeah, so as opposed to this, so sort of on the opposite end of this, you could try to do something different, which is called canonicalization. In this case, instead of averaging over the entire group, we average over basically one element in the group. So here the idea is, instead of taking my input and averaging over the entire orbit, I pick one element from each orbit. Sort of, in words, you transform the input into some canonical position before you pass it into the neural network, right? So this function C represents this canonicalization, and it has the property, or the properties we want it to have is that, well, it basically collapses every orbit to a single point in the same orbit, right? And this, again, it's easy to verify, is going to be a projection on invariant functions, so you get this preservation of being a universal architecture, right? So so let me give some examples of canonicalizations, just to give you an idea, a specific idea of what I'm talking about. So for example, for our situation of this symmetric group acting on point clouds, we could, for example, sort the input lexicographically, sort by the first row, use that to essentially standardize the input. Or for example, for rotations acting on a bunch of vectors in 2D, we could rotate the first non-zero column to the x-axis, for example, or you could rotate the longest column to the x-axis. These are examples of ways to canonicalize the input. Okay, so, and in fact, a bunch of things have been proposed, a bunch of canonicalizations have been proposed, including methods for learning canonicalizations using a different neural network function.
Will you need to assume some regularity of the canonicalization, like continuity or something?
That's exactly what we're getting at, right? So yeah, so the issue with canonicalizations is that they, as we'll see, they don't preserve continuity, right? Even if the underlying neural network function is continuous, the canonicalized function typically is not going to be continuous. And exactly, we want to understand when you can have a continuous canonicalization. But before I get to that, I want to also mention another kind of generalization in between canonicalization and group averaging, where what you do, and this is was called frame averaging in the literature. What you do here is you say, well, given an input x, I have some function to a non-empty subset of my group. So I basically, instead of averaging over a single element or averaging over the whole group, I average over some subset that depends on my input. This is frame averaging, right? And so to construct the frame average function, you do exactly that. You average over some input-dependent subset of the group, right? And so And so another question, right, is can this generalization here preserve continuity in the cases that we're interested in? Okay, so first let me start with a trivial result here. So of course, the canonicalization preserves continuity, meaning for any continuous function, the canonicalized function is continuous if and only if the canonicalization itself is a continuous function. And if we go back to these examples that we looked at before, typically they're not going to be continuous. I mean, one exception here is, for example, if you have the symmetric group acting on Rn, so you have one-dimensional points, then sorting is a continuous canonicalization. The sorted vector is a continuous function of your vector. However, it's easy to see that if you sort lexicographically, or for example, if you rotate the longest vector to the x-axis, it's not going to be continuous. So, the first question we looked at was, when can you construct a continuous canonicalization, specifically in those instances of permutations and rotations and orthogonal transformations acting on point clouds? And it's not too difficult to show that if you look at the action of the symmetric group on point clouds, you can't do it unless you're in dimension 1. Okay, it's a little bit more difficult to work out what happens for rotations and orthogonal transformations. In this case, for orthogonal transformations, if the number of points is less than or equal to the dimension, there is actually a continuous canonicalization. But if it's bigger than d, there is no longer a way to continue to canonicalize the input. And for SOD, for rotations, the number of points has to be strictly less than the dimension in order for there to exist a continuous canonicalization. Otherwise, there does not. So this indicates that this approach of canonicalization fundamentally isn't going to be able to preserve continuities. And that might be a problem, right? So we should try to do something else which does. So what about this frame averaging approach? Right, so if you use these frame averages, can you construct these in a way that preserve continuity and ideally have a frame that's not too big? So it turns out, again, for the action of permutations on point clouds, you can't really do it. Your frame has to basically just be group averaging. And also for the action of SOD, at least in dimension 2, we have not fully completed a proof in higher dimensions, but I think this is enough to argue our point, right, is that even in this case you can't even have a finite frame which preserves continuity. And so really the issue with this frame is the fact that if we think back to the definition, that you're averaging with equal weights on all of these group elements. So it's an equally weighted average. And that's actually what causes these results to be true. So the generalization that we propose is something called weighted frames, and something similar was also proposed in a previous paper by this guy, Pozniakov. Although what we really do is to connect this with continuity and show that it does allow you to preserve continuity while other methods don't. So the issue we have here, right, is neither canonicalization nor frame averaging can preserve continuity unless you kind of average over the whole entire group. So the generalization that we consider is, well, we allow averages with weights. I mean, in words, that's exactly what it is. So we have a map here. Instead of from X to subsets of G, we map X to a probability distribution on G. So there's some input-dependent probability distribution on G. And so we have conditions on this map that guarantee that the averaged function, so we define then the average function to be the value at the input X is the average over this input-dependent distribution of f of gx, right? We basically average with respect to that distribution f of x. And so we have conditions. We in the paper we derive conditions on the on this weighted frame that guarantee that this will be an invariant function, and that also guarantee that it preserves continuity. The condition that it gives you an invariant function is basically that this weighted frame has to be roughly equivariant up to an element of the stabilizer. That's essentially what it means. So I won't write down exactly the conditions. They're a little bit technical, but not very difficult. The main point is, however, that, so we also define the size of the frame as the maximal size of the support of this probability distribution. Right, so for example, if this map F maps every point X to the uniform distribution over the group, right, that's group averaging. If it maps every point X to some Dirac delta, that would be canonicalization. And here now we just essentially map each point X to some probability distribution and take a weighted average depending upon the input X. Okay, so our goal is going to be to see or determine whether there exist small-sized frames that do preserve continuity. Basically, let me just essentially present the results. So in the case of the action of permutations on point clouds, we can construct a weighted frame of cardinality growing like n to the 2 times d minus 1, which preserves continuity. And for rotations and orthogonal transformations, we can construct a frame of cardinality n to the d minus 1, which preserves continuity. Now, these are still very large frames, right, n to the 2 times d minus 1, but it's a lot less than n factorial, which would be averaging over the whole symmetric group. And n to the d minus 1 is also fairly large, but it is at least finite, and one could deal with it. In practice, because these frames are still very large, we implement things empirically, right? We do not exactly calculate this average, but rather we sample some points from this input-dependent distribution and then take an empirical average, right? So it's some sort of kind of generalization of data augmentation. And let me remark also that we do not know if these are the smallest weighted frames that will work here. We don't know if these are the smallest weighted frames that can preserve continuity. The only lower bound we have is that in the case of permutations, it has to grow linearly in n. For rotations and orthogonal transformations, we only know it has to be bigger than 1. In other words, that no canonicalization exists. So perhaps there are even better things you can do here.
So for Lie groups like SOD and OD, is this closely related to like quadrature schemes?
Well, I don't know what just happened. Okay. Yeah, so I guess maybe this connection broke down, or. Yeah.
It's frozen on what's being recorded. It's the same as
Everyone's
that.
frozen. Okay.
Try just unplugging it from the machine.
Sure.
There we go. And then put it back in.
Okay.
You've got it like extended as a preview.
It was in preview. Yeah, it would show it over here. I think.
That window thing. Okay. I'll have to, if you can, I'll have somebody come here in just a second. I'm not exactly sure.
Okay. Yeah. That's all right.
Give me just a second.
Sure. I guess to answer your question.
You can't share your screen? Or what happened?
On my screen, it's I don't know. This is fine.
It's like
yeah.
frozen, so it's just like the video, and then I don't think it's recognizing the desktop, like that as an extended display, like how when we started, so it almost like it went away. I'm not sure.
Oh, you
Okay.
Oh, okay.
There you go.
Cool. It's way too big, but. Okay. Yeah. So to get back to your question, actually, I'm not sure. I'm not sure. I don't think so. Related to quadrature, it's kind of. I mean, the way that. Well, so. It's in some kind of playback mode, or. Oh, okay. I see. I think I know what I did. Right. Okay. So yeah, so to answer your question, I'm not sure. I mean, basically the way that this frame is constructed is so I'll describe the permutation in a second, but the yes, the orthogonal transformation one, for example, is done as follows, or the SOD one is done as follows. I can describe how to sample from the frame. What you do is you look at the lengths of all of your vectors, and you sample them based upon their lengths. So like the probability of picking one is the length divided by the sum of the lengths. And then once you have that vector, your next vector is obtained by looking at by projecting orthogonal to that guy and doing the same thing. And then the next vector is obtained. So you can then sequentially sample a sequence. Once you hit d minus 1, there's a unique rotation that's going to take the original guys. There's a unique rotation that's going to take those guys to, like, the first one to a multiple of x1, the second one to something in the x1, x2 plane. You basically perform in some Gram-Schmidt, essentially, on that sequence. And that determines the rotation. And it turns out if you sample like this, the resulting frame will actually preserve continuity. Yeah.
Yeah, so it doesn't sound so related because it's data dependent somehow.
Yeah, you have to make it data dependent in order to get things to be continuous. Yeah. Sure, yeah.
These are the lower bounds?
So only in this case we have a linear lower bound. So yeah, it's we would like to know what the minimal size weighted frame is, but it seems to be kind of a difficult topology problem. At least, yeah. So these are our best upper bounds. Our best lower bounds are linear here, basically d minus 1 times n minus some lower order stuff, and here just bigger than 1. So we know there doesn't exist a canonicalization, but we don't have a lower bound better than that. Yeah. So it's possible there may be something much better, which would be quite interesting. Yeah. So here, so I described the SOD frame. Let me describe the frame for permutations, which is very, in some sense, kind of similar. And the idea is, it's easiest to describe the frame by explaining how to sample from it. So for a given input x, you choose a random direction in the sphere, right? Choose a random direction, and then you take a permutation which sorts your vectors along that direction. Okay, so I mean, for example, this lexicographic sorting, right? We basically sorted. We chose the permutation to sort like e1 times x. You know, the first standard basis vector dot x1. So of course, if you choose any fixed direction, this is not going to be continuous, right? But it turns out that if you average over all directions, so if you pick a random direction, sort in that direction, plug that into your network, and then average over all random directions, a continuous function will be, again, will stay continuous under this averaging. So that will preserve continuity. And you can count that the number of possible permutations that can occur in this way is on the order of n to the 2 times d minus 1. So that's where this bound comes from. And you know, when we use this frame in our experiments, we basically do the sampling. You know, we sample a random direction, sort along that direction, and use that. Okay, so finally, let me show a simple experiment to kind of demonstrate why continuity, I think, will be important. And let's start with the MNIST data set. Of course, a kind of trivial problem at this point, but I'm going to make it harder for the network. Instead of feeding it the image, right? Instead of feeding it this array of pixel values, I'm going to turn this image into a point cloud. So I'm going to turn this image into a list of 100 points in 2D, right? Where I'm basically sampling from like the where there's ink on the in the image essentially, and then randomly permute those. So the neural network gets this 2 by 100 matrix as input, whose columns are the coordinates of a bunch of points in some random order that lie inside this image. And based on that, we want to classify what digit we have, right? So obviously this is permutation invariant, and that's the, it's not really rotation invariant, so we're only considering permutation invariance in this experiment. And basically what we do is the following. We just take some base architecture that's, of course, not invariant, in this case just a feed-forward network with 3 hidden layers, and then we use different methods to make it invariant, right? So we don't make it invariant. We consider the lexicographic sorting, which is discontinuous. We consider this SN continuous weighted frame, and we consider this Reynolds operator. This is another name for group averaging, and see how each of these perform in terms of the test accuracy. So we train them all for the same amount of time. It was like 60,000 iterations. So recall that the weighted frames and group averaging, we can't really do those exactly because that would be too expensive. So we implemented empirical sampling to implement those with from 1 up to 25 samples that we tested. So more samples means we're evaluating this average function more accurately. And the point of these results is that so if you don't build in the invariance or you average over the group, you don't get good results because the group's way too big. It's like 100 factorial. This is doing the data augmentation in this case is doing nothing. It's essentially the same as having no invariance. Somehow the neural network does still learn something. It gets 25% accurate instead of 10%, but doesn't perform very well because there's just not enough information in the data, right? Since you don't have the invariance built in. Once you build in the permutation variance using, for example, a discontinuous canonicalization, you get much better accuracy. However, losing continuity does hurt you a bit because if you build in the invariance and continuity, we're able to get ultimately a better test accuracy. Although, to be fair, we do have to average over quite a few samples in this, when we empirically implement this frame. So it is more expensive, but perhaps it will be useful in these situations. So this experiment essentially mainly demonstrates that it is important to preserve continuity and invariance kind of at the same time, that you can get better results by doing that. Of course, this experience for the permutation group. For the permutation group, there are very good invariant architectures like deep sets and transformers, so you wouldn't want to actually do this in practice. However, I think these frames will be much more interesting for rotations where it's a lot harder to design invariant architectures. Let me conclude here and just sort of mention some open problems, which one of them is we don't know what the smallest possible frames here are. And one can also ask whether, here we only talked about preserving continuity. Perhaps you may also want to preserve differentiability or higher order derivatives. I think that probably is more of a theoretically interesting problem, but we don't know how to do that in the best possible way either. So thank you guys for your attention. And happy to take
Questions for Jonathan?
So what do the weights look like? Are they closer to being uniform, or are they closer to being concentrated on?
So that's a good, it depends on the input actually. Like for example, for permutations, right? Basically if you look at your points in say R2, then you look at a bunch, you basically would look at all the pairwise differences between 2 points. That kind of divides up your plane into a bunch of segments, right? And the widths of those, the angles of those segments are the weights corresponding to certain permutations. So depending upon what the input x is, it could be very uniformly distributed, or it could be one permutation is taken with a much higher probability. So it's input dependent.
I think that equivariance and symmetry is very important, so I don't mean this to be a totally adversarial question, but like the DeepMind team found that equivariant architectures were not a win for AlphaFold. That was the motivating example that you started with. So do you have a feel where give any insight as to like when, I mean, it's not, I agree, your intuition seems very reasonable. Do you have any thoughts on that, or?
Well, yeah, I mean, so I mean, what we're trying to do now is trying to find problems where this actually is useful. So I mean, this toy example, of course, is not something that's useful, but we're hoping to try to find examples where we can show that like this does actually get better results than not doing it. And I mean, one thing that you could,
The Baker
yeah.
Lab team, I mean, it was a quark was put on a Rosetta fold, but then that got kind of crushed by AlphaFold.
Yeah, I mean, it may be that in those cases, I mean, the thing is, one advantage of this method is you can apply it to any architecture you want. Like that, you could take whatever AlphaFold did and do this on top of it and see if it helps. But of course, it will increase the expense because you'll have to sample from this weighted frame. So yeah, I mean, I don't know. I find it hard to believe that not building the invariance is really better, but you can't argue with empirical results, right? So, yeah. I mean, that's a good question, and yeah, we're still trying to figure out how to kind of make this actually really useful. Yeah.
Any other question? Okay, let's thank Jonathan again.